11. Once you get the idea with 11, it turns out to be not a difficult problem at all. We just need to think about what's going on in order to make this happen. I think in the homework I introduced an additional variable which limited the possibilities. I think there are a lot of possibilities on values of a and b, a lot of ordered pairs, a and b, that would make this a continuous function. It's piecewise defined, and we're going to think of it as a function of x. There's some unknown constants a and b. I like to establish a relationship between a and b that will guarantee that this is a continuous function. Different values of a and b would give us different continuous functions, so I'm not just talking about one function. It's kind of a function whose definition depends on the values of a and b, but we'd like to choose it in such a way that it's a continuous function at 1 as well as everywhere else. So it is a polynomial, x squared plus 5ax, for all values less than or, well, let's say less than 1, also equal to 1, but in particular less than 1. And it's a polynomial. A linear expression defines it, ax plus b, at all values greater than 1. So since it's equal to a polynomial, on each of those open intervals, it's going to be continuous everywhere less than 1 and everywhere greater than 1. The big question would be, what happens at 1? Where the two pieces meet, are they going to meet at a common point, or are they going to miss each other? And we want to figure out a and b in such a way that they meet rather than missing each other. So what we need is this. We need the limit of f of x as x approaches 1 from the left to equal the limit of f of x as x approaches 1 from the right. I'm pretty sure both limits are going to exist because it's a polynomial either way. There's not a concern with vertical asymptote or any kind of bizarre behavior, regardless of how we define how we choose a and b. So the limits are going to exist. We just need them to equal each other. Now let's see how we would evaluate these limits. If x is a little less than 1, approaching 1 from the left, x is going to be a little less than 1. We define the function using this expression. If x is 0.5 or 0.8 or 0.9, we would use that expression to define the function. So we would substitute into that expression. So to evaluate the limit as x approaches 1 from the left, we would say this is the limit as x approaches 1 from the left of the expression x squared plus 5ax. Now, if we didn't specify that x approaches 1 from the left, I wouldn't be able to indicate it's that quadratic expression. I just wouldn't know. If x is a little more than 1, and we're going to evaluate this function, we would use that expression because that defines the function if x is greater than 1. So this would be the limit of the expression ax plus b as x approaches 1 from the right. Now, since these are polynomial expressions, we can evaluate each limit by direct substitution. We can take the 1 and substitute it for x, and it'll, in each case, give us an expression in the variables, or yet to be determined constants, a and b. So it's going to be it's going to be 1 squared plus 5a times 1 for that limit, and it's going to be a times 1 plus b for that limit. And we're not going to be able to single out a particular value of a or particular value of b because we have two unknowns, but just the one equation. There's no other constraint on this. So just simplify. 1 plus 5a equals a plus b. And whichever might be easier, solve for a in terms of b or solve for b in terms of a. I'm thinking, since we have b kind of all out there almost by itself, it would be easier to solve for b in terms of a. So I'm going to subtract a from both sides to get 1 plus 4a equals b. And so there we go. B equals 4a plus 1. How about that? Now the function is defined at 1, and it's going to be defined. It's going to be defined to be the value of this limit as x approaches 1 from the left. So as long as I ensure that that's equal to the limit of f of x as x approaches 1 from the right, it's going to be continuous. So I need both of the one-sided limits to exist. I need them to agree, and I need the function to be defined to be this at 1. But for any choice of a and b, f of 1 is defined, and it's defined to be 1 squared plus 5a times 1. So it's going to equal this limit. If I didn't have the or equal to bar, it would be undefined at 1, and there would be no way to choose a and b to make it continuous, because even if we cause the limits to define the limits so that they were equal and the pieces of the graph met, there would still be that hole. So I have to have the or equal to bar in order for it truly to be continuous. I don't know. How does this answer feel? B equals 4a plus 1? I don't know. Is that the least bit unsatisfying? I'm going to... Okay. So here is basically our piecewise function. That's how I defined these objects. Not too many objects there. We've got f of x equals x squared plus 5ax if x is less than or equal to 1, and ax plus b if x is greater than 1. And for different values of a and b, this is a different function. The graphs look different. We just want to choose a and b so that they satisfy the equation b equals 4a plus 1. So how about if we start with a equals 0? If a equals 0, what would b be? B equals 1. 4 times 0 plus 1 is 1. So how about a equals 0, b equals 1? What's this going to look like? A equals 0. Okay, so what function does that give us? 0x plus b. And if b equals 1, are the pieces going to meet? Yes, there we go. So a equals 0, b equals 1, the pieces meet, and this particular function is continuous. We want a different function, but choosing a and b in such a way that it's continuous. What if a equals 1? If a equals 1, what would b have to be in order to make it continuous? 5. 4 times 1 is 4 plus 1 is 5, so b needs to be 5. Whoops. Come on. Should bring the mouse. There we go. B equals 5. That makes it continuous. And maybe one more. What if a is -3? There we go. A is -3. What would b have to be in order for this function to be continuous? Negative how much? 11. -11. Let's see if I can go that far to the left. Negative... There we go. -11. And so the pieces come together and meet there. So it's... I give it the name f. F really should be kind of qualified, maybe f with a little double subscript of a and b, because the function itself depends on the values we choose for a and b. But if we choose the right values so that there's that relationship between them, then it will produce a function that's continuous at 1 and, of course, continuous everywhere else.